we will be studying about electric field lines. For a point charge plus q and its electric field, let us introduce a unit positive charge at a point n1 in the electric field of q. As both the source charge and the test charge are positive, this unit positive charge placed at point n1 follows the path n1a in the electric field due to the repulsive force on it exerted by the electric field of the source charge. Thus, path n1a represents an electric line of force or an electric field line. An electric field line represents the path followed by a unit positive charge in an electric field. Now, if we repeat this procedure for various points in the electric field, we obtain the electric field lines around the charge. Electric field lines are used to represent the electric field of a charge or a system of charges pictorially. In fact, the electric field lines follow the same direction as the electric field vector at any point in the electric field. Since electric field line is the path followed by a unit positive charge in an electric field, if we draw all the electric field lines for the electric field of the given source charge q, the electric field lines appear as shown. Electric field lines help us estimate the electric field strength. The relative density or closeness of the field lines at different points gives an indication of the relative strength of the electric field at those points. The field strength is stronger at places having more crowded field lines than at places where they are less crowded. To illustrate this, let us now consider two regions, P and Q, of same area placed normal to the field lines in the electric field. The field lines in region P are relatively closer than those in region Q. The number of field lines passing normal to an area is proportional to the magnitude of the electric field strength at these points. This indicates the strength of electric field at P is greater than that at Q. As the electric field strength is stronger at region P than Q, as the field strength varies from region to region. To understand the dependence of field lines on area, let us understand the relation of the area of the element and the solid angle created. It is important to note that solid angle is a measure of a cone. When the intersection of a cone with the sphere of radius r is considered, the solid angle delta omega subtended by the area element is defined as delta s by r square, where delta s is the area in the sphere, which is the area element cut out by the cone. Let us label it as equation 1. Therefore, delta s is equal to r square delta omega. Let us label it as equation 2. For a given solid angle, delta s, the number of radial lines, is the same. At two different points, say A and B in the electric field, which are at distances r1 and r2 from the charge, we had seen that the area of the elements subtending the same solid angle, delta omega, will be delta S1 is equal to R1 square delta omega at A and delta S2 is equal to R2 square delta omega at B, respectively. The number of field lines, say n, passing normal delta S1, delta S2 is also the same. the number of field lines passing normal to a unit area is equal to electric field strength E. Therefore, the electric field strength E1 at A will be equal to the number of field lines per unit area at A, which is equal to N upon delta S1 or N upon R1 square into delta omega by using the value of delta S1. Let us label it as equation 3. Similarly, the electric field strength E2 at B will be equal to N upon delta S square or N upon R2 square into delta omega. Let us label it as equation 4. If we divide equation 3 and 4, we see the ratio of electric field strength at A and B is equal to R2 square upon R1 square. Hence we can conclude that the electric field strength due to point charge varies inversely to the square of the distance from the charge. From the equations 3 and 4 we see that even though the number of field lines N and solid delta omega are the same at A and B, the electric field strength E, which will be equal to number of field lines per unit area, is proportional to 1 upon R square, where R is the distance of the point from the charge Q.